All right, good. Because I wasn't going to answer them anyways. So the next two topics are the two coolest topics in this whole class. And of those two, this is probably the one that's most, that's going to be useful in the most cases. So the new topic is two-dimensional linkages. And linkages are collections of rigid bodies connected by joints. So this is an example of a 2D linkage. The 2D just means that everything moves in the plane. So let's say that there are pin joints connecting all these things. And then there's some known force vector applied here. And let's say that you apply some known couple here, 100 Newton meters or something. What are the angular accelerations of the individual bodies? And so you might imagine, linkages are the basis for machines, robotics, calculations in biomechanics, and probably a bunch of other stuff. So yeah, this is a super useful topic. The difference, what do you call, so that's a linkage. What would you call it if I put, let's say, another bar here that connected it there, and now this thing couldn't move? A bar connecting this joint to the wall, and now you could apply all these loads and that thing would be stationary. Yep. A truss is a kind of structure. So generally structures. So if it's a static thing, it's a structure. And if it moves, it's a linkage.
Those members?
Yes, that's right. And so let me give you sort of the overall process for a linkage, and then we'll just do a couple of examples. So first, number each member in the linkage, just for bookkeeping. And then second, one by one, isolate the members in the linkage and use Newton's laws. If the member has a fixed point, If it has a fixed point, do you use Newton's second law or not? Right, so if it has a fixed point, you're not going to use Newton's second law. And so the rotational Newton's second law gives one equation. If the member has no fixed point, then Newton's second law and the moment equation you get two equations for Newton's second law, one for rotational, and so three equations. Yep. Okay, so our inertial coordinate system is fixed to the wall, right? It's stationary compared to the wall. So this and this both have fixed points. Those don't go anywhere in the coordinate system. This and this are fixed to, they're attached to other members, but those points move as this thing rotates up and down. Okay, so the question is it fixed in the inertial coordinate system? When you're done with all the members, so when you've done every member, you think you have enough equations to solve? How would you know? I'm going to tell you. No, you don't have enough. You don't have enough equations. And so the extra equations come from joint constraints. Okay, so now you've used Newton's laws for every member. You still have more variables than equations. And the last step is at each joint that's not fixed, so that's what we were just talking about. So in the example up here, two of these joints are fixed points. We don't have to worry about those. But two of them are not fixed. And in those two that are not fixed, the restriction that we have to say basically is there's a point on this member that, that joint is a point on this member, okay? And that joint is a point on this member. And the acceleration of the point on this member has to be equal to the acceleration of the point on that member. Just saying that those members can't fly apart at the joint, okay? They have to stay in the same place. So the acceleration according to one attached member must equal the acceleration according to the other attached member. And these accelerations come from the watermelon equation and relative motion. Okay, so like for example, you'd get an equation that says like the acceleration of the center of mass of member 2 plus alpha 2 cross some r, let's say this is a joint P, say 2P. These don't really mean anything right now. I'm just saying that, so according to member 2 now, I'm writing the acceleration of that point at the joint. And then we have to set that equal to the acceleration of that point according to member 1. Okay, so how many useful equations would we get out of this at one joint? It's a two-dimensional problem, so these accelerations are in 2D, so each one of these would give 2 more constraint equations. And one more thing, I mean, we're going to go through a bunch of examples, but how would it be the case that, so I'm saying, like, let's say that in this example, I'm doing the constraint for this joint here, okay? And so I'm saying the acceleration of that point according to this member is equal to the acceleration of that point according to this member. Why would it ever be the case that I would, so on this side, I'm using obviously circular motion, but also relative motion to calculate the acceleration of that point, okay? And over here, I'm using circular motion, but no relative motion. Why would it be the case that on one, I would use relative motion? Yeah. Yep, that's exactly right. So if you're doing, so if you're calculating the constraint equation at this point, in order to calculate the acceleration of that point according to this member, you don't need relative motion because it's moving around this fixed point, okay? So you don't need relative motion. For this one, neither of those 2 points is fixed. Nothing on there is fixed that we know of. So you need to calculate the acceleration of the center of mass and then use relative motion to add on the circular motion part. Okay, so yeah, the 2 things you're going to use are circular motion and relative motion. You won't always need relative motion. Yes, that's right, exactly. So relative motion, this you're only going to need for members with no fixed point. Okay. Here's a bookkeeping rule. assume that the joint itself, usually we'll be talking about pin joints, so the pin itself. Assume the joint itself is part of the lowest numbered member that it connects. Okay, so let me describe what I mean here. This is the same idea that the people who took statics from me, this is how we did it in statics. And let's say that this one that has a fixed point is member 1, and this one with no fixed point is member 2. Okay. Then this joint connects member 1 and member 2. Okay, so we're going to assume that the pin itself is part of member 1. Okay, and that means that if you had forces applied to the pin, which happens in these a lot, you treat that as that external force is something that's applied to member 1, but not applied to member 2. Okay, it's just a bookkeeping thing. You could use the exact opposite rule of that. The only thing you can't do is if you have a 500 Newton force acting at that pin, treat it like it's 500 Newtons acting on this one and 500 Newtons acting on this one. Okay. All right, so let's start out with sort of, this is the kind of simple calculation that a lot of biomechanics studies start with. So let's say there's a hinge on the ground and a member with 45-degree angle. So say that angle is 45 degrees, and then a pin joint connects that member to another one that's perpendicular to it. Let's call these joints A, B, and C. And this angle is 45 degrees, and this is a right angle. And I'll call this member 1 and this member 2. And let's say that the external load that's applied is 100 newtons this way. Okay, so if you made the lengths and masses of these things, relate to a leg, and maybe you put a extra mass up on top to show, so that you can sort of simulate the body being there. This might be sort of a simulation of the kind that you'd want to calculate, like the kind of joint forces that would be caused by this injury or whatever. Okay, so let's say that the length of both of these is 1 meter. And let's say the mass of both of them is 5 kilograms. And let's say at this instant, omega 1 and omega 2 are both negative 10 radians per second. And we want to calculate, well, let's start by just calculating the angular accelerations of both of these members. Okay, so first of all, what's happening with that? Let's think about what's happening with those angular velocities. So -10 means those are both rotating clockwise. Does it make sense that these are rotating clockwise when the only force, well, there's a weight force, I guess, but, and then this force is pushing this way? It does. That's kind of like a trick question, misleading question in a way, because any velocities, so Newton's laws say that forces and moments relate to accelerations and angular accelerations. They don't have any relationship to velocities. Velocities you can think of as being caused by integrating the accelerations through time up until that instant. Okay, but what happens, the loads that are applied at that instant don't have any instantaneous effect on the velocity. Okay, so basically what this means, if these are both rotating clockwise, it means that up until this instant, loads had been applied that made them both rotate clockwise. And then right at this instant, maybe this load got switched out for this one. Okay. And so now physically, what does it mean that these both have the same angular velocity clockwise? What's this doing? Here's the distinction that I want to make. I think probably to a lot of people, you would think, okay, member 1 has an angular velocity of 10 radians per second clockwise, and that's right. And then a lot of people would think member 2 is rotating clockwise at 10. So the whole thing's rotating down, and the angle between these is getting bigger. But that's not what happens. That angular velocity, every angular velocity you get for a body is relative to the coordinate system, not to what it's attached to. Okay, so that omega 2 doesn't have anything to do with this. And so in other words, the angle between those is actually staying the same. Okay, and the whole thing is just tipping down that way. So remember, angular velocities and accelerations are given with respect to the coordinate system. So this has two members. They're already numbered. And so now we're just going to isolate the individual members and go through the rigid body process for each one. So I'll start with member 1. And we'll just go through the steps for a rigid body. Does member 1 have a fixed point? Yep. And so the about point is the joint A. And so step 2, we can calculate the mass moment of inertia. So I sub A is equal to 1/12 times 5 kilograms times the length squared. But that's the mass moment of inertia about the center of mass. So now we need the parallel axis theorem. So that's plus 5. And then what's the distance? 0.5. Yep, it's the distance from the center of mass to the about point. And so 0.5 squared. And so 5/12 plus 1.25. What is it? 1. kilograms meters squared. And now free body diagram. There's a weight force acting at the center of mass. That's 5 times 9.81, so 49.05. The pin joint applies an unknown force vector. I'll call that RA. And then the pin at the top applies an unknown force vector from member 2. So I'm going to call that the force on 1 by 2. And there's one more thing. Since we always assume that the pin is connected to the lowest numbered member, that 100 Newton force is applied to member 1. And so now rho, force, moment. So first I'll do the force RA. That is the about point. So the rho vector is 0. The force vector is RAX, RAY, and the cross product is 0. And then the weight force, the rho vector is 0.5 times cosine and sine of 45 degrees. So that's 0.3535, 0.3535. The force vector is 0, negative 49.05. And what's the cross product?
Minus 17.34.
Minus 17.34. And then the force F12. The rho vector is 0.7071, 0.7071. The force is F12x, F12y. And so the cross product is 0.7071 F12y minus 0.7071 F12x. That's not a vector, that's just, I was running out of room. And then there's one more force, the 100 Newton force. It has the same rho vector as F12. The force vector is negative 100, 0. And so the cross product is positive 70.71. So Newton's second law says RAX, RAY plus 0, negative 49. Oh, we don't need this. Step 5. We don't need Newton's second law. Step 6, rotational Newton's second law. So that says negative 17.34 minus 0.7071 F12X plus 0.7071 F12Y plus 70.71 is equal to the mass moment of inertia, 1.6 repeating, times the angular acceleration of body 1. Okay, so we only have one useful equation from this, and that's always the case for the bodies with fixed points. So I'll set that aside as equation 1 star. I'm going to move all the constants over to the right side. So we have negative 0.7071 F12X plus 0.7071 F12Y minus 1.6 repeating alpha 1 is equal to, what's 70.71 minus 17.34? 53.37 negative. And we have one equation, 3 variables, so we can't solve it yet. So we're just setting that aside for our big system. Now we'll go to member 2. Okay, so member 2 is the top member. Does that have a fixed point? No. So the about point is the center of mass. And so the mass moment of inertia, I guess I'll just, I'll call this like just the mass moment of inertia for body 2 is just 1/12 times the mass times the length squared. And I think that's 0.416 repeating. And now a free body diagram. There's a weight force of 49.05. There's no force at the top. At the bottom, member 2 is connected to member 1. There's the force on 2 by 1. But if we call it F21, then we've introduced new variables we don't need to introduce, and we definitely can't do that. So we need to use Newton's third law, and this is equal to negative F12. And now that's not introducing any new variables. And that 100 Newton force doesn't apply here because it's applied to the pin, which we said was connected to member 1. We're treating it as part of member 1. Force, moment. So first, I'll do the weight force. That's at our about point. So the row vector is 0. The force is 0, negative 49.05. No moment. And then the second one is negative F12. The row vector there is 0.3535. negative 0.3535. The force vector is negative F12x, negative F12y. And the cross product is negative 0.3535 F12y minus 0.3535 F12. Do we need Newton's second law for this one? Yeah, no fixed point, so we need it. So we have 0, negative 49.05 plus negative F12x, negative F12y is equal to the mass of the body times the acceleration of its center of mass. And we don't know anything about that. So these are new variables. I'll call it A2, X and Y. So remember, this is the acceleration of the center of mass of body 2. And then the moment equation says negative 0.3535 F12x minus 0.3535 F12y is equal to 0.416 repeating times alpha 2. And so this one we got 3 useful equations. For our system of equations, these are equations 2, 3, and 4. So I'll call this one 2 star. Says negative F12x minus 5A2x is equal to 0. Equation 3 star says negative F12y minus 5A2y is equal to 49.05. And then equation 4 star says negative 0.3535 F12x minus 0.3535 F12y minus 0.416 repeating alpha 2 is equal to 0. So now we have 4 equations. And how many variables do we have? Well, here is something you have to be careful about. If you look at the free body diagrams, you would get the wrong number of force variables, because look at what happened with number 1. We had 2 unknown force vectors, and they both appeared in the table. But since this one has a fixed point, we didn't use Newton's second law. And so even though this appears in the free body diagram, it's not in our system of equations. We could solve for it later if we want. But from our first equation, we don't have any RA, and we also don't have any acceleration. All we have is the force vector F12 and the angular acceleration alpha. Okay, so we have 3 variables in the first equation. And then in the next 3 equations, that's not new, but we do have the acceleration. So let's start writing these down. So how many variables do we have? We have F12, we have alpha 1. Those are from the first equation. And now from the next set of 3 equations, we have the acceleration of the center of mass of 2. And we have the angular acceleration of 2. So 4 equations, 6 variables. Well, the way it's always going to work out is how many joint constraint equations are available to us. We never have to do joint constraints at ones that are fixed. So even though there's 2 joints, this is the only one that's useful to us. Okay. And so the difference between our number of variables and our number of equations just exactly matches the number of constraint equations. Okay. So we need 2 more equations, 2 constraint equations. And we'll get those from joint B. And so this constraint equation is going to say basically the acceleration of B according to member 1 has to be equal to the acceleration of B according to member 2. Okay, so first member 1. This is just, so if we're calculating the acceleration of this point using this body, that's just a simple circular motion because this point is fixed. And so A is fixed, so we don't need relative motion. So the acceleration of the point B, according to member 1, is 0, 0, alpha 1, crossed with the R vector. The R vector goes from the center of the circular motion to the point we care about. So that's the vector from A to B. So that's 0.7071, 0.70710, plus the angular velocity that's given at the start of the problem. So that's 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross 0.7071, 0.70710. So what do we get here? This one is going to be negative 70.71, negative 70.710. And this one is going to be minus 0.7071. 0.71 alpha 1 plus 0.7071 alpha 1, and then 0. So this whole thing comes out to be, this was round off here, 70.71. Okay, so negative 0.7071 alpha 1 minus 70.71, and then 0.7071 alpha 1 minus 70.71, and then 0 for z. Any questions about that one? Yep.
Can you just step back to the fact that acceleration would be about 1, I think, but acceleration would be about 2?
Yeah.
Okay. I'm not seeing that.
So we're just saying that, so this joint B is a point on member 2 and it's a point on member 1, right? And so we're just saying that if we calculate the acceleration of that point on member 1 and calculate the acceleration of that point on member 2,
Okay.
those have to be the same. If they're not the same, then it's flying apart, you know? So we're restricting it to move together.
The angle between those two not changing.
The angular,
90s.
according to the velocities, it's staying the same. We will see that there are different angular accelerations, I think. I don't really remember for sure. But, I mean, you can imagine, like, what's going to, so velocity-wise, it's staying the same. But acceleration-wise, this force is going to make this start to, you know, open or whatever. The angle's going to start getting bigger. So they're not going to have the same angular accelerations. It's like if you're running and someone smashes into your knees do that. That's a rude thing to do, though. I'll tell you that. Okay. So next time, okay, this is as simple as a linkage problem can get. I can't think of a simpler one than this, and so these take a long time. Eventually, if you're doing this kind of work, you're writing software that does this stuff. You're not doing these calculations by hand. But next time we'll do member 2, and then we'll solve this system. Okay, that's all.